Hello, everyone. Bonjour. Welcome to the day 3, the last day of the MWA project meeting and the session 1 on galactic and extragalactic science. So the first presentation is going to be an overview of galactic and extragalactic group activities from the MWA by Chris Risley. Yeah, welcome, Chris Risley.
Let's get that. On about there. And then hopefully that sound is coming through nice and clearly. Great. Allora, bonjour à tous, grazie und guten Morgen, e finalmente buongiorno a tutti e tutte. And I'm sorry I don't speak great or Romansh, but 3 out of 4 is not too bad. Yes, I am Chris Risley. I'm from the University of Bologna, and I am also the MWA Principal Scientist. And today I'm here representing the Galactic and Extragalactic group. And so I'm going to be giving you a high-level whistle-stop tour through all of our activities and all the science that we do. So firstly, what is GEG? What is the Galactic and Extragalactic group? Essentially, we do the science that is not covered by all of the other science working groups. The MWA has 5 science working groups, which we've heard from in previous days: EOR, pulsars and fast transients, who we'll be hearing from a little bit later, solar, heliospheric, and ionospheric, and GEG. We cover everything not covered by everyone else. Specifically, science-wise, we have teams who work on galactic continuum, studying our own galaxy, moving further afield. We have people who study nearby galaxies in the Magellanic Clouds, people who study radio galaxies of all varieties, AGN and star-forming varieties, clusters in the cosmic web, which is my own personal science case, and we have teams who work on polarimetry and spectroscopy as well. And beyond that, GEG also is really the umbrella under which several of the main MWA surveys sit. That's GLEAM-X, sort of our wide shallow survey, and the Midas and Gold fields, which are the more narrow, if you can call an instrument like the MWA with its fantastic field of view narrow field, but much, much deeper. And so I'm going to be touching on all of these topics. A little bit of management stuff. Previously, we were led by Chinoa Tremblay, who was the chair of GEG until the end of last year. Currently, Stefan and myself, in our capacity as principal scientist and deputy principal scientist, we are shouldering the responsibility of being the chair of the GEG group until a new chair can be onboarded. And there was me speaking at the MWA's 10-year anniversary last year in Australia. We published a lot of papers, to date 58 collaboration papers and 80 papers using public data. So fully 36% of MWA papers come from our science, which is a nice and impressive statistic. And we do a lot of work with students, supporting students. So far, 18 student theses have been completed successfully from the course of the MWA's history. So let's start with surveys. Let's go from the big projects then to the science cases specifically, because a lot of our science is built on the backbone of, built on the back of surveys. I could hardly talk about surveys without mentioning GLEAM, which occurred during the phase 1 of the MWA and led to many fantastic science results. But what we're doing at the moment, the spiritual and physical successor for GLEAM is GLEAM-X, the extended GLEAM survey using the extended MWA configuration. The first data release came out last year, and the second data release, the paper is in press, and it's covering this deeper pink area that you can see here in this figure from Kat Ross's paper. Kat Ross has really been the driving force behind a lot of GLEAM-X's results. We also have people who are doing projects like cosmology with GLEAM-X. Here are a couple of figures from the source counts and angular correlation function from GLEAM-X DR2 from Venville et al. In preparation. And essentially, we are looking at the brightest source population here. So really, we're looking at an AGN-dominated population in the source counts. And broadly speaking, the source counts angular correlation functions are consistent with what we expect from previous studies and consistent with lambda CDM cosmology. There's also other projects that are building on underutilized aspects of GLEAM, such as the 300 megahertz, because the original GLEAM survey was performed with all of the MWA's frequency bands, including 300 megahertz. Stefan is leading this Herculean effort. It's an underutilized but extremely scientifically valid and valuable component of GLEAM because it really extends the frequency space up into a unique region. And Stefan has a talk on this a little bit later. And touching briefly on deep surveys, Midas and Gold, here's a really fantastic wide field deep image. Don't worry about seeing too much in there. It's a wide area and there's lots of largely unresolved sources, but we're talking about deep observations of the gamma fields. We are getting to sub-Milijansky RMS at sort of 216 megahertz. Nick Seymour's the PI of that project, but Sean Patterson is doing a lot of the data processing there. And here are some statistics from Gold. So Midas is sort of deep, and then Gold is ultra deep on the gamma 23 field. And getting down to an RMS, I don't know whether you can read the numbers at the back there, but we're talking 0.28 millijanskys per beam RMS, getting 100 plus sources per square degree. And this puts Gold really on par with the kind of survey depth that we are getting from things like EMU and the other sort of deep surveys at higher frequencies with ASCAP. So this is some really cool stuff. This is going to be a fantastic science archive. Polarimetry, this is also a field that is near and dear to me. Polarimetry, we are talking about studies of cosmic magnetism. Specifically, we're talking about using the linear polarization of radio sources to study magnetic fields in the universe on large scales. This is some work that I did a few years ago using GLEAM to do the first all-sky RM synthesis survey. It was a massive revolution because at long wavelengths, you get really precise rotation measures. So you can use low-frequency astronomy, low-frequency polarimetry to do precision magnetism studies. The drawback of POGS was that it was a completely aftermarket bespoke processing. This is something that is being taken care of as part of POGS-X. A lot of thought and care was put into this. And so POGS-X is fully commensal with the main GLEAM-X data processing. And significant improvements primarily from resolution and the improvements in the primary beam model are the big wins. And so here's a couple of examples of one specific source known as the exclamation mark source, because this bright spot at the bottom is extremely bright. It's got more than a Jansky of polarized flux at 200 megahertz, which is crazy bright. But if you can, I don't know how well you can compare the spectra from sitting where you are, but all of this crud at low rotation measure here in the phase 1 in POGS is due to beam model inaccuracies and errors. And so with the improvements in the beam model that are being used in POGS-X processing, you get significant reduction in instrumental leakage. And so you can do RM science a lot deeper, a lot more precise, and just a lot deeper and a lot more precisely. So getting into the science groups, spectroscopy, which the topics we cover here is things like astrochemistry, looking for redshifted H1, but from radio galaxies rather than EOR signals, radio recombination lines, and things that are near and dear to Stephen, for example, SETI. So one of the many highlighted things that has been fun over the MWA's lifetime is opportunistic searches for SETI signals from interstellar visitors. When Oumuamua flew through the solar system, Stephen used the MWA to look for signals, didn't find anything. It's a rock, it's not a spaceship. Chenoa Tremblay has done many targeted SETI surveys, and here from this paper, you can see the MWA occupies a really interesting and unique niche in exploring the parameter space. And a couple of years ago, Chenoa did a study of known exoplanets towards the galactic center, searched 144 different known exoplanet systems, but there were no plausible detections. And so Chenoa and collaborators were able to put pretty stringent limits on SETI signals. Talking about astrochemistry, Chenoa has also spent a lot of time doing molecular line studies, looking for nitric oxide and various other molecules. Here's an example of a couple of detections of, I think it was nitric oxide here, but Chenoa has also done broadband studies using the MWA's excellent frequency coverage. Here's one study towards one particular system, and all the green lines represent known molecular lines, but there were no detections in this particular study. Galactic continuum, we've got so much to cover. Diffuse galactic emission, H2 regions, and supernovae are the name of the game here. And so we've seen this in Natasha Hurley-Walker's paper from a few years ago, using the MWA's different frequency bands to create color composite maps. You can easily start to identify things like H2 regions and supernova remnants because they look very different in the color maps due to the spectra. Studies of the galactic center, and also you can see there the shadow of the moon during an observing run. But Natasha followed this up more recently, looking at the galactic center lobe. Here, we're really exploiting the MWA's key capabilities in terms of its rich surface brightness sensitivity, its fantastic bandwidth to make these color composite maps where we can instinctively identify the physics of what's going on, the field of view, and the extensive rich archives. And so in this study, particularly focused on the galactic center lobe, the fact that it goes dark shows that we are seeing a low frequency turnover. The spectrum is brighter at higher frequencies, so we have a low frequency turnover. This represents thermal absorption against the continuum emission from the galactic center. And emissivity arguments put this galactic center lobe at a distance of around 2 kiloparsecs, which was incompatible with previous interpretations. And so it's reshaping our understanding. In terms of supernova, one of the key capabilities is also the fantastic synergies we have with Rosetta. Supernovae are interesting because we're talking about shock acceleration, which is something that goes on in a variety of different environments in the universe, and supernovae drive chemical enrichment and gas mixing in the interstellar medium. And in the Milky Way, we're missing sort of around 700 supernovae if you use various different arguments. But the MWA has been quite effective at searching for and finding various of these other ones. So this is one from a paper by Silvia Mantovani, who will be giving our next talk about supernova hunting with the MWA. You can see the MWA continuum image on the right at 200 megahertz, and a composite of MWA in blue and Rosetta X-ray in green. And so you can see the extended X-ray. Shell here, representing the hot gas inside the supernova, and then you've got the shocked material expanding outwards. And this is a pretty hefty supernova. We're looking at something that is 1.7 degrees across, so we're really tapping into the MWA's angular scale sensitivity. On even larger scales, although I forget exactly how big it was, there's the Hoinga supernova remnant, which is another one that was found and really characterized nicely using Rosetta, which you can see on the left there in red, and the MWA data, which you can see there in color on the right. I've highlighted the shocked material from Hoinga there on the right-hand side because it's a little more difficult to see. They've had to use advanced imaging processing techniques to subtract out all of the contaminating diffuse emission and upweight the diffuse sensitivity. But this is something that the combination of phase 1 plus phase 2 data will prove very powerful for. So the MWA really is giving us detection and characterization of very, very large supernova remnants on scales of much more than a degree. And there's several more of these in the works. There's a paper by Miroslav Filipovic and collaborators that's currently in peer review on another very large supernova remnant. The name of the game in the longer term here is to go to the phase 1 plus phase 2 joint deconvolution, which was demonstrated here by Natasha on the Vela complex. Because phase 2 gives us the excellent high resolution, and phase 1 gives us the sensitivity to very low surface brightness material. So when you combine the two, you can clean deeper, you can recover all the scales, and you can do some really fantastic science. And this is something that Silvia is working on as well. Here's one example supernova remnant from the galactic plane survey that Silvia is working on. This is actually just phase 2 at the moment, but in this study, Silvia found 12 new candidates and 9 supernova confirmed, and there are 77 H2 regions to be examined. So there's rich physics coming from this survey. And catch Silvia's talk next to learn more about the hunt for supernova of various different varieties. Magellanic Clouds and nearby galaxies. So this is an area that was experienced a lot of activity in phase 1 and has gone through a little bit of a lull in phase 2. But represents an excellent opportunity for some new work and a breath of fresh air. We're talking about studies of the LMC and SMC using radio continuum tracers and correlations between H2 and H alpha. to study star formation rates. Al-Saberi et al. Used these data to study supernova remnants in the Magellanic Clouds, and also Miroslav Filipovic used some of these data to explore the extragalactic source population behind the Magellanic Clouds. These papers are several years old, but they are representing some nice work. Nearby galaxies, jet recollimation physics is something that the MWA also really techs into quite nicely, because we get nice resolution for these nearby jets. This was a paper by Velovic and collaborators looking at jet recollimation in NGC 2663 and trying to answer the question of, are we looking at episodic jet activity, or are we looking at a slow jet in a low density environment? And then studies of radio halos in nearby galaxies, studying physics of cosmic ray streaming and various other things. I'm going to have to speed up. Cool. This is really good. Basically, I'm trying to emphasize here, there's a lot of science that was done with phase 1, and there's so much we can do with phase 2, and particularly phase 3 data. But there's an opportunity for fresh people to get involved here. Radio galaxies. I could hardly talk about radio galaxies without mentioning Sen-A, but I'm not going to talk about it. I just wanted to show that image. It's very big on the sky. There's a paper that's currently in review on M87 Virgo A by Linhui Wu and collaborators, using broadband data from 72 gigahertz to 3 gigahertz, studying the turbulent lobes and the filaments and edges, and both integrated spectral modeling and modeling of the spectra in different regions. You can see the fantastic coverage from the MWA combined with other data sets allows us to really explore the injection and aging processes, get precise measurements of the synchrotron timescales and things like that. This paper should be coming soon to an archive near you. I also love doing a bit of shameless self-promotion. Here's some work that I'm doing on a nearby giant radio galaxy, looking at feeding and feedback in galaxies. And so here's a couple of examples from the MWA that I've done recently at low frequencies, combined with Meerkat and some compact array data that I managed to make some very nice images with using advanced imaging techniques. We've got data covering 72 megahertz to around 7 gigahertz, plus we have VLBI observations. So we're in the process of doing a comprehensive aging study of this source from parsec scales to the megaparsec scales of the lobes. And really what we see is we've got a very young core that's about 10 mega, switched on about 10 mega years ago, but the lobes themselves are ancient with spectral ages of over 300 mega year. And showing the color composite image here with some examples of the spectra, this is where it gets really interesting, because while the lobes integrated show a power law spectrum, when you go to resolved studies, it gets much more complicated. And so you've got the brighter regions, which are, with the yellow colors, are nearer to the site of injection, and going to the more purple colors go further downstream. You can see that as you go downstream from the injection site, spectrum gets much steeper and starts to curve dramatically, which is what gives us these high spectral ages. But you can see that in the steepest regions of the south lobe, for example, which the emission sort of sweeps up here, we don't even see it, but we struggle to even see it with the MWA at 200 megahertz, which gives you an idea of just how steep the spectrum is. But also in the north lobe, in the very bottom part of it here, something interesting is going on physically, because we see the spectrum steepen and then flatten again, which perhaps suggests we're looking at different components superimposed along the line of sight. This is just a nice demonstration of what we can do with these broadband data, combining both phase 1 and phase 2 data. Various studies of radio galaxies looking at other radio galaxies, looking at jets and disk wind interaction, looking at flaring, sources with unstable periodicity and quasi-periodic signals. Essentially, this study from Wang et al. Showed that the instabilities in the accretion disk act to influence and modulate the accretion rate and have an impact on the jet launching. It's quite an interesting study combining MWA and VLBI data. I could also hardly mention radio galaxies without talking about Kat Ross's work on spectral variability. Kat has spent a long time using the MWA's broadband data to study the variability of peaked spectrum sources, and this is one of the gold standard examples that over the course of several years really varies very significantly at low frequencies, but not at all at high frequencies. And so Kat's work is Kat is working on understanding the causes of this, what is causing these changes. And so here's another example from a paper by Kat last year, where she was working on linking the spectral variability and substructure. Here's one source that showed significant variations in the low frequency spectrum. But when you go to VLBI frequencies, it's this source on the right-hand side here. So this source is actually, despite the fact that it has changed dramatically at low frequencies, you might expect evidence of substructure. But at VLBI resolution, it was completely unresolved. So actually, the interpretation was that this is a blazar-type source that was caught in, or quasar or blazar-type source that was caught in the act of flaring and has since calmed down. But some of the other ones in the sample, like this source, show quite significant substructure. And so that's linking this, it's linking the substructure at VLBI resolution with these broadband spectral changes. And the idea is testing the youth versus frustration hypothesis. Finally, clusters in the cosmic web. I think I've left myself enough time to talk about this. The MWA is fantastic at identifying big, fluffy, steep spectrum things. So here's a couple of examples from the paper by Torrance Hodgson and collaborators. I think this is still the steepest low frequency spectrum measured. With the MWA, there's this very curved spectrum, but if you fit a power law to the central points, it's got a spectral index of -6, which is bonkers. In another cluster, some work I did with Stefan, there's this very steep spectrum fossil, and at low frequencies, the spectrum is already quite steep at sort of -2, but the high frequency component of the spectrum is insanely steep. It's -8, which is just very, very steep. How does something have that kind of spectral index and not already be switched off and how is it still detectable? And we see this in some other clusters as well. This recent paper by Pete McGregor and collaborators looking at steep spectrum diffuse emission and filaments in Abell S1136. And really what we're looking at here are things like fossils, threads and filaments in clusters. These are representing the very last light of AGN that have long switched off, and the only reason they're still detectable is because they're in a cluster environment, which provides this additional source of pressure, sometimes gently reaccelerating or adiabatically compressing or slightly shocking this fossil plasma and keeping it just visible. But questions still remain, like what are the nature of all of these filaments that we're detecting everywhere in clusters? Are they shock fronts? Are they magnetic ropes in the ICM? Whatever it is, these are inefficient, weak particle acceleration mechanisms that are only accessible at low frequencies. I've got two more studies to show you before wrapping up. One that Stefan is leading on Abell 194, and here you're seeing the MWA in cyan and meerkat emission at 1.28 gigahertz in red. But if I can show you images, a few slightly different images, to emphasize what we're talking about, there's the fantastic radio galaxies here, and there's plenty of filaments that have been identified. But the interesting emission that probably doesn't come out on the projector is the cyan emission that extends all the way out here. There's this very large-scale diffuse sheet that you can see here in the MWA maps on the bottom. Not even LOFAR really recovers it, and meerkat sure as heck doesn't. So this is steep spectrum emission, and we're trying to understand what is the nature of this? What are we looking at here? And some very preliminary spectra show quite steep spectral index for this diffuse sheet. So at low frequencies, we see a spectral index around -1. But when you take a common in a UV cut and include the meerkat data, the limits on the meerkat data, we get a much steeper spectral index of -2. And we're going deep. Stefan is working on going deeper into this with even deeper data, even more broadband data. So we're tracing the effect of cluster weather on AGN and looking at these broadband spectra, which tell us about the physics of particle acceleration in these environments. And looking really at gentle acceleration on hundreds of kiloparsec scales. How does that happen? We're trying to understand. And finally, my last cluster, a little bit of shameless self-promotion. Abell 3667 is the cluster that we're studying here. It's the gold standard Southern Hemisphere cluster. The MWA did some work on this in 2014, and then I did some work on it in 2015 with Cat7, the meerkat precursor. But we've got new MWA data across the full MWA band. We're seeing 3 frequencies here with ASCAP's data there. This is phase 1 plus phase 2 jointly deconvolved deep data. And we see so much of the cluster volume is full of diffuse radio emission. Showing it in color composite so I can talk a little bit about it some more. We see the well-known features, the Northwest Relic, which has this curved morphology, the much fainter and more compact southeast relic, which is down here, the embedded radio galaxies, such as this FR2 that has this tailed radio galaxy, the tail extends at high frequencies, we see up to about here, but at low frequencies, it goes way, way further out into the intracluster medium. We also detect the halo for the first time at low frequencies, and we also knew we detect downstream emission from the northwest radio relic. The entire cluster is full of steep spectrum diffuse radio emission. So we're trying to understand the physics of what is going on there, the hostile environment for galaxy evolution, the AGN tracing cluster weather. You can see the spectra here, but I won't talk about them too much. The take home is that the MWA is perfectly suited to studying cluster environments because we just get all of the faint diffuse emission across a broad bandwidth. And so wrapping it up, GEG, what do? We leverage all of the MWA's strengths to do our science. Our science is lots of sources. Our science is individual objects. It's nearby objects. It's the most distant galaxies, bright stuff, very faint, fluffy emission, clusters, giants, dwarves, clouds, and basically our science is everything along the way to cosmic dawn. There's a lot of active development going on. We're responsible for a lot of new calibration and deep imaging techniques, validation, post-imaging corrections, and new source finding and characterization routines. We're a very open and active group, so come and join us and do some stuff. Come and have a chat. Find us in the breakout session if that's your jam. And thanks for listening. I will take questions here.
There been any study or is there dual chain, like following up optically selected or very selected dual chains? But I think there's not much in terms of this, right? In terms of dual chains, this is very interesting also for the connection when it's.
So for those on, yeah, thanks. For those online, the question was, are there any existing projects looking at following up specifically dual AGNs identified from primarily optical studies to see if there's any interesting physics or any statistical differences between dual AGNs and single AGNs? The short answer is, to the best of my knowledge, I'm not aware of any specific projects on that, but that is exactly the kind of thing that we can do and the kind of thing that we should be doing once GleamX gets fully completed. And it would be very interesting to take some examples of nearby ones, because then we can really leverage the resolution that we have to the best.
I was closing your talk about agent feedback. What's the redshift of this?
This giant radio galaxy. Yeah. So that is this giant radio galaxy just shown in color composite. It's 0.028, so it's very nearby.
Those other galaxies, redshift between 1 and 2.
Oh, between redshifts of 1 and 2, I don't think we have the resolution to do that really. I'm not sure off the top. I couldn't really give you a limit, let's say, to the upper limit to the redshift. In this example, ESO 422 is very nearby and it's very extended on the sky. It's 1.5 megaparsecs across, but it's almost a degree on the sky. So it's very nearby and we can leverage the resolution very well.
A bit on technical side, since you guys seem to go deepest with the imaging, what is the current best, deepest, like lowest noise image that you can get with MWA? And is it like hitting the limit, or would you be able to go even further?
I think to the best of my knowledge, the deepest image we have is the one from Sean Patterson that we're showing. Natasha's just posted in the comment about 300 microjanskis per beam, 0.3 millijanskis per beam. So that is about the deepest we're getting. Sean's work with Midas, Natasha's just commented. Thank you, Natasha. It's been a long time since I've looked at the math of what the confusion limit is like at this frequency and resolution. Natasha might be able to answer that better off the top of her head than I would. But we're pushing We're pushing very deep, and we'd like to see how deep we can get. That's really the point of Midas and gold, to see just how deep we can get.
We can take one more question. Any questions online? Right, last chance. Josh, just add a comment again.
We are dominated by side lobe confusion, but classical forms a measurable component of the noise that we are seeing in surveys like Midas and gold. Yeah, side lobes are a pain.
There are no more questions yet. I'll give it one more last to Chris. Thank you, Chris.
Thank you.
So next topic is going to be constructing a new data set for detecting supernova remnant candidate. Oh, sorry. All right. The next topic is going to be constructing a new data set for detecting supernova remnant candidates by Silvia Montovani. Hi, Sylvia. Can you hear us? It's not. Check.
Can you hear me now? Okay, I think
Yeah, we can hear you.
Perfect, thank you.
And I'll just give you a 5 minutes warning at your 10th minute.
Yeah, okay, perfect. So before beginning, I would like to thank the organizer for giving us the possibility of participating online. My name is Silvia Mantovanini. I'm a PhD student at Curtin University in Western Australia. And for my PhD project, I am imaging the galactic plane with the aim of finding new supernova remnants in our own galaxy. In this talk, I will explain to you the process of imaging the plane and what were the challenges that we encountered so far. So the service that I'm using for imaging the plane are Gleam and GleamX. I'm pretty sure that you're all well aware of what they are, but I will just briefly give you some information about their main properties that are interesting for this project. The GleamX pipeline is described in the GitHub repository that you can see here in the slides. They have been collecting using the matrix multiplicity array, the MWA, in 5 different frequency channels, from 72 to 231 megahertz, and scanning the sky in 7 declination strips. Gleam was observing using the phase 1 of the MWA, so we had an abundance of short baselines that enables the survey to resolve larger scales between 2 arc minutes to 15 degrees with a resolution of 100 arc seconds, and we reach a galactic RMS noise between 50 to 100 millijansky per beam. Instead, GleamX was observed after the upgrade of the telescope to the phase 2. We doubled the baselines, and so we reached a resolution of 35 arc seconds, resolving in this case smaller scales, so from 45 arc seconds to 20 arc minutes. And we don't have an RMS noise for the galactic plane yet, but the extragalactic noise has been reduced to 1 millijansky per beam, which is almost 6 to 10 times lower compared to the Gleam one. So the main goal of the PhD is combining these two data sets to leverage the resolution and the sensitivity that these two surveys have to offer, and so detect remnants in all the different angular scales that we have available. My pipeline is strongly based on the GleamX pipeline and is described in a GitHub repository that you can see in the slides. I would just have to change a few things, and I'm describing here in the slide. So first of all, I have to select the data. I select the region of the sky and I pick all the observations that have a point in center within 5 degrees from the galactic plane. And I'm using both, as I said, Gleam and GleamX because we want to fill in all the different angular scales. And I'm also using all the 3-hour angles so that we can have a better UV coverage. Then for all the observations that I'm selecting, we need to make sure that the quality is actually good to go in the final stage. So I need to perform some quality checks. I start with the RFI flagging, followed by calibration, which could either be an in-field calibration or we can transfer solution from a calibrator observing during the same night. If a bright source is present in the field of view or outside the field of view, we could either perform a self-calibration or a sources subtractions. And then we finally go to the imaging stage, which is the first time where we can actually visualize the data that we are processing. And so we can see whether the calibration solution were properly applied, if there were artifacts from bright sources, or if the RMS is high or low, and so on. Then we perform some post-imaging corrections, which are position correction and flux density scale corrections as well. If they all pass the test, we move to the final stage where we are trying to deconvolve all the observations together using image domain gridding, which is a new algorithm that I will describe a little bit later, to get the final image. And for every single region of the galactic plane that I'm doing, then I will mosaic them together to have the final image of the galactic plane. So in these and the following slides, I will illustrate some of the problems that we encountered during the processing. First of all, we had some leftover RFI in the lowest band of the MWA, so between 72 to 103 megahertz that our normal flagging algorithm couldn't resolve. We tried a couple of different methodologies, and the one that works better is the one that I'm showing here in the slides, where we are working with the visibilities directly. So we are calculating the median of the visibilities for every single channel and the median of the medians for a window of 55 channels at a time. And we are flagging all the channels that have median value, which is greater than 0.5 sigma, the median of the medians. And you can see in the top right plot the channels that have been flagged for these particular observations and how the quality of the image has greatly improved from before and after the application of this flagging stage. The second cause of issues is the presence of bright sources in our field of view, which is quite ironic because I'm trying to image the galactic plane, which has most of the brightest and diffuse structures that we have in the sky, but some sources are actually more challenging than this, such as Centaurus A. We try to apply a self-calibration only on the source, but this doesn't seem to have ideal results. So we try to subtract the source, so we apply a self-calibration and a subtraction of the source. And how this works is that we change the position of the phase center in the position of the source itself, and we try to image a little box around the source, and then we subtract the visibility from the model data. We had to increase the size of the box that we were using because it wasn't quite big enough to include the whole size of Centaurus A, but this actually caused a divergence in our image. So for this reason, we try to reduce the number of the minor iterations in our cleaning process, and this seems to bring the galactic plane back, which was great, but the quality is still not ideal. So what we decided to do is to go back a little bit and just apply a self-calibration only with a reduced number of minor iterations, and the quality is actually already a little bit better. We have less artifacts from Centaurus A, but the RMS were still quite high, and so we went back to the normal settings that we have, just with a reduced number of minor iterations, and this actually is the best results that we got so far. We don't have to apply all these steps for all the observations, but just in the case where Centaurus A is actually in the field of view of our image, if it is on the edge, it doesn't really matter because we can subtract this as it won't be included in the final IDG image. So it is challenging, but sometimes we can get rid of that. And then another interesting issue that we had is for the GleamX observations. When I opened these images, I was quite scared. This is caused by the fact that GleamX is particularly focused on the smaller scales that we have, and in the galactic plane instead we have the contribution of a lot of diffuse emissions, and we use the multi-scale scale bias parameter to separate the contribution of the different scales when we do our images. By default, this is set to 0.6, but if we increase it just to 0.7, the results are actually pretty impressive. So we can give less weight to the diffuse emissions and focus on the smaller details that are relevant for the GleamX data. The final correction that I had to apply was during the fits warp call that we use for astrometric corrections. How it works is that fits warp takes the position of the sources that we have in our image and it compares with the position of the sources in a well-known catalog. The catalog that we're using is composed by a subset of the MVSS and SAMS surveys, which have been collected at 1,300 megahertz and 843 megahertz. But as you can see from the slides, we are missing quite a large region of the sky where obviously the galactic plane resides. So we actually need to fill in this gap to have reliable corrections. And to fill in the gap, I'm using RAX, which is another radio surveys collected by ASCAP at approximately 888 megahertz. We are selecting a subset of this catalog in the region that we are interested in, and we are selecting only the brightest parts and unresolved sources. So with no internal matches between 3 arc minutes and an integrated to peak flux density ratio lower than 1.2. During this stage, we also create plot where we're showing how the position of the sources is shifted, and this helps us to identify and exclude all the bad observations, so where the ionosphere was actually turbulent or calm. And in the slide here, I'm giving an example of a bad observation. You can see how the position of the sources is kind of not following a pattern, and it's quite wide. Instead, this is an example of the good observations. And it's also quite interesting if we stack one next to the other, all these plots, we can see how the ionosphere is changing over the night. When we're done with all the quality checks, we finally get to the final stage of the IDG cleaning. IDG, image domain grading, is a new algorithm implemented in WS-Clean, which operates pretty well on GPUs and operates directly on the measurement sets. To be able to correct the images, we need to provide a configuration file where we have to specify the direction-dependent corrections that we want to apply. And in particular, I am applying the LDM screens, which saves the offset position of the sources and the beam. In the panel, I'm showing
5 minutes warning.
Thank you. In the panel, I'm showing a simple application of the IDG. So the first little cube on the left corresponds to the gleam, where you can see all the diffuse emission of the galactic plane, but the RMS is quite high in the background. Instead, the middle panel represents gleam X, where the RMS is quite low, and we can see the fine details of all the structures. Instead, in the last panel correspond to the joint convolution of the first two ones. And we have the best from both the surveys, so all the diffuse structures that we're interested in and a low RMS noise. So the aim is to image the galactic plane that we can see from MWA with galactic RMS noises from 2 to 10 millijensky per beam across the observing band, and we will be able to resolve scales from 45 arc seconds to 15 degrees. So we will have a good sample of supernova remnants to identify and study. We had to adjust the parameters for our IDG call, so we changed the pixel scale from 0.6 to 0.5 divided by the frequency channels, and we changed the Briggs parameter we set to an average value between what we were using for GLIM and GLIMX. And then, as I said, we need to specify an internal configuration file, and we changed the pointing center to match the mean value of all the pointing centers that are going into the same IDG cleaning code. This is another example of application where we have the Vela supernova remnant. As before, the first panel corresponds to GLIM, then we have GLIMX and the joint deconvolution, where we reach an RMS of 5 millijensky per beam in the middle band of the MWA, which was quite good. And finally, one of the results of my work, this is a small region of the galactic plane where it is an RGB, so we have 3 images in 3 different frequency bands overlaid, one on top of the other one at 121, 154, and 185 megahertz, and we have respectively an RMS noise of 9, 5, and 4 millijensky per beam, which is quite good compared, for example, to the same region in GLIM, where the RMS noise was 45 times bigger than the one that we have now. And you also have to consider that at the end, This is just a small section of the plane, and I'm moving 5 degrees at a time towards the galactic center. So because the MWA has a quite wide field of view, we will have a lot of overlaps when I'm going to mosaics all the images together. So we are expecting these values to decrease even further. In the image, you can see heaps of sources. The one that I'm interested in are the supernova remnants that I highlighted here in green. And I also highlighted the non-H2 regions, which are star formation regions that are the one that cause the most confusion when we're going to detect new supernova remnants. And I also overlay the pulsar catalog because it's quite interesting to see whether we can associate one of the pulsars with supernova remnants. Another interesting study that we can perform at low frequencies is the absorptions that is caused by the thermal absorption that is caused along the galactic plane. So we can better disentangle the contribution from H2 regions that are thermal sources from non-thermal ones that are our supernova remnants. As you can see from the little zoom in, the H2 regions are popping out in a bluish color in opposition to the reddish that correspond to the synchrotron emission. And also we could construct spectral index map, and we can highlight regions inside the remnants itself of absorptions, or for example particular elevations. Thank you so much for listening, and I'm happy to take any questions.
Any questions? Oh, that's nice. Any questions online? Right. Yeah. One last chance. All right. Okay. Thank you, Sylvia. And we'll move on to the next presentation, which is going to be. Oops. Yeah, the next presentation is going to be the Galactic and Extragalactic All-Sky MWA survey at 300 megahertz by Stefan Duchesne. Did I promise it right?
Perfect. Yes. Thank you.
Welcome. Stage is yours. I'll give you a 5-minute warning.
Sure. Just try and clip this because I'm really bad with microphones as well. How's that sounding? All good? Okay, good, because I'm usually quite quiet.
Sorry.
On the bottom? Alrighty, there we go. Cool. Yes, so I'm Stefan. I'm a research scientist at CSIRO in Perth, Western Australia. Also happen to be the deputy principal scientist for this here collaboration. And I'm going to be talking about this somewhat small addition to the GLEAM survey at 300 megahertz. So we have already heard quite a bit about GLEAM, but I will just briefly point out some of the relevant aspects that are going to be mentioned a bit later on. Particularly, the original GLEAM was observed from 72 to 231 megahertz in the 5 sort of standard frequency bands, which we now call the standard GLEAM bands. If you ever go through a proposal, those are what they are. It was observed through this meridian drift scan strategy, where you point the telescope up at some declination on the meridian and then let the sky drift over for 2 minutes, repoint after cycling through all frequencies. So we end up with quite a few of these 2-minute snapshots, which are all processed, calibrated and imaged independently and then stacked later on. And there's also this nice big wideband image that's created from the top 2 bands, simply just averaging them together, which is typically used as the main reference image for source finding. And if you ever look at images of GLEAM, it's probably either going to be a 3-color RGB image like the one on the right, or it's going to be the 200 megahertz wideband image. So obviously go check out the 2 main GLEAM description papers if you're interested in any of the sort of more finer details. But there was also an additional set of observations taken a little bit later on between 2015 and 2016, which incidentally is about when I got into radio astronomy. So it's kind of a fun little timeline project for me. But these are all phase 1 data as well. Pretty much observed identically, but at 300 megahertz, and with some additional strips of declination covered just because the field of view is quite a bit smaller at 300 megahertz, so you need a little bit more data to cover in the otherwise insensitive regions. So it ends up with about 12,000 snapshots, and that's kind of why I got silver in the download competition, because those were all downloaded at least once during this project, so that's where most of it comes from. But there were no observations that cover the South Celestial Pole, so that's going to be an interesting little bit that I'll talk about later of working out how to actually deal with that. And each strip typically has about 5 nights of observing, and that will come into play a bit later on as well. So 300 megahertz stuff has generally been kind of tricky to deal with. Calibration is quite challenging at that frequency, and there's also just a lot of RFI that we need to flag as part of trying to get useful data out of it. And so some work by Jaden Cook, who was an honor student at the time, he spent quite a bit of time working out a fairly reliable strategy to get good calibration solutions for the 300 megahertz observations, starting with sort of pilot work looking at calibrator scans, which are done daily by the observatory, which is obviously very handy. And you can probably see why it's a bit tricky if you look at the primary beam response shown in the top 2 figures. So the top left panel there from Jaden's paper shows a zenith pointing, which is typically where the primary beam is most well behaved, and it still has incredibly strong side lobes, or fairly sensitive side lobes, that you have to actually contend with and deal with when you're calibrating and imaging. But then as soon as you start pointing off zenith, those gets much worse and gets to the point where the side lobe and main lobe basically look the same, and that's kind of a bit of an annoyance. So Jaden did manage to get some really nice images out at around about 2 arc minute resolution, 30 to 50 millijansky per beam noise. For phase 1 data, that's fairly reasonable, I think. And this really helped to showcase we could actually process these data, particularly for a full survey. So that's moving on to actually processing all of those 12,000 snapshots. I do process these with a fairly standard continuum pipeline. Of course, as Stephen mentioned on Wednesday, all the processing we do for MWA is functionally no different to any other interferometer. There's just a few little bits and pieces here and there that will be a little bit different, and there's some specific points in the 300 megahertz processing that was a little bit different than what I would normally do. So I'm going to focus on a couple of points, mainly this kind of annoying calibration strategy, and also the post-imaging corrections for the brightness scaling. Otherwise, everything else, flagging, which is a huge amount of flagging in these data, but otherwise the flagging is fairly normal. Peeling of sources and side lobe subtraction is fairly straightforward at this point for continuum processing, and the imaging is basically exactly the same. And just for reference, all of this processing is done on was done mostly on Garawala and a little bit on Satonic, since we've been slowly moving over from Garawala with that coming to end of life at the end of the year, and it's fully CPU for this particular bit of processing. Just that seems to work fairly well for us at the moment. So the calibration strategy is, it's in principle fairly normal for MWA data. We either find our best in time and nearest in time calibration solutions and apply them, or we take a solution from a bandpass calibrator. And in fact, Sylvia mentioned a similar strategy used for the galactic plane processing. If your in-field calibration doesn't work, then you fall back on your bandpass calibration scans that are done daily. The problem is those bandpass calibration scans are not always applicable. Sometimes they do actually degrade as a function of time over the evening or over the night of observing. And sometimes they don't even calibrate at all. So it's a bit of a challenge. So the process to actually get this to work reliably for the whole survey was to basically do both and choose the best one by making a very quick image and looking at the statistics in that image. And that's the only way I can make this reliable. And for me, when survey processing, that's what I like to see, reliability. I don't want to have to handhold every single obs ID or every single observation. So it's reliability is key. And this process, while a little bit tedious, works fairly reliably. So the interesting point that differs a little bit to how I would normally do data processing for MWA is in the way I've done the brightness scaling for this particular survey. What I found after comparing the flux densities of sources in the 300 megahertz data to the Gleam model, which we actually use for calibration, is that there is time-dependent fluctuations, and these typically trace where you change your solutions and whenever bright sources perhaps fall into those solutions that maybe don't have the perfect model. And so the bottom plot there shows a whole declination strip worth of obs IDs and observations, and you can see the kind of nights each day or night separated into little chunks there. And so if you look at a couple of the days or nights, you'll see that there's these nice big changes in the ratio of the 300 megahertz flux density to the model flux density, and that's basically what we're correcting here. The simplest way I found this to work, again, reliably is just to fit a somewhat standard arbitrary polynomial to these little chunks of time, just to avoid these big steps in these ratios. And this works, again, fairly well. So once we've got the 12,000 mosaics, 12,000 snapshots processed, ready for mosaicing, I've taken a slightly different approach to the mosaicing process than what Gleam normally does. So with Gleam and GleamX, the strategy is to make a mosaic a whole declination strip. These produce quite large images, and it makes sense when you have a very big field of view, of course. For the smaller field of 300 megahertz, I found it's fairly straightforward to make a slightly smaller mosaic region. This, for me, makes it a bit easier to manage data. I like lots of small images than one big giant image, which might sound counterintuitive, but it works nicely for me. So the process here is just to generate some regions, make some mosaics centered on those regions, and then run source finding. So there's a few extra steps in here, including rejecting snapshots or observations with the moon, which there are actually quite a few of, high noise, and also very large beam as well, ignoring all of those just to make sure our data are looking fairly reasonable, and then running source finding on those mosaics. So I'm just going to show a couple of examples of what they look like, and hopefully the color scale works out nicely. Seems fine, cool. This is probably one of the nicest ones. This is one of the full regions, not cropped. Has Fornax-A, of course, and probably has the lowest RMS noise in the entire survey. It looks really nice. We can keep going a bit further south. Things start getting slowly rattier as you get further south, but it's mostly fine. And here's ABAR 3667, which Chris mentioned in the GEG update talk as well. Continuing further south to our nearby galaxies, LMC and SMC there. Again, still looking fairly nice. If you've been looking very carefully, you might notice the beam is slowly getting slightly bigger. That's fine. And then we'll go further north and start looking not so good. But most of the northern stuff actually looks fine. I just want to showcase this one because this is another one of these bright sources, Crab, I think, where things tend to fall apart a little bit because we don't do self calibration. And the Crab model is always a little bit iffy when it comes to in-field calibration. But otherwise, this actually looks fairly similar to what it looks like in the original Gleam data, so I'm not too concerned. Now, I did mention the South Celestial Pole was not covered in observing, in that there was no actual pointings towards that, which I think is just a technical limitation of the instrument. Someone can probably correct me on that. But turns out actually the zenith strip, the declination minus 27 strip, has side lobes that lie at about dec minus 86, and you can image those and actually get fairly decent images. So I imaged all of them, and despite them only being about 30% the sensitivity of the main lobe, you can get some nice images, and once you stack them, they actually produce a pretty good mosaic. So the process actually remains identical for this imaging, except you just phase rotate to the side lobe before doing everything, and it works really well. And the mosaic for that looks a bit like this. It's not quite as nice as everywhere else, but it's still fairly sensitive. It seems fairly reasonable as well in terms of flux scale and everything else. You do get some interesting features creeping in, like these fun rings, which I believe is just RFI, and a few of these larger scale undulations as well, which can be removed with certain types of filtering. The one issue, of course, is that we don't have perfect coverage, so there is a little bit of a gap between the lowest declination strip at minus 72 and the side lobe, and so you do end up with a bit of a ripple in sensitivity, but it's only about a factor of 2 or so, so it's not too concerning, and still not much of an increase in noise compared to other regions of the survey anyway, so it's mostly fine. So once we have all the mosaics, we then have all these individual source lists for each mosaic as well, and then we just stitch these together. We end up with about 296,000 sources with this current iteration of the catalog, with just under a little bit less if we exclude the galactic plane. On the top right there, you can see the noise map. So this is the local RMS measurement at each of the source positions, binned as in heel-pick spinning scheme. And you can see that it's fairly reasonable for most of the survey. There's a couple of regions that are a bit worse for wear. The Crab region we saw before is one of them, and there's a few other ones as well that kind of creep in. The galactic plane, of course, doesn't look super nice. It's not really the purpose of this survey. That's the other one we heard about just before. But otherwise, things look fairly reasonable. Median noise being about 7 millijansky per beam, resolution around about 2 arc minutes, and that also varies a little bit as a function of position over the survey, which is what the bottom 2 plots show. So this is about where I'm at with this particular project, which really is something that started with me getting very carried away with processing. But I'm at the point of actually validating the data, which is, of course, very important if we actually want to release this and have people use it for things. At the moment, I've mostly been comparing against other surveys that are around about 300 megahertz or up to 400 megahertz. And actually, if anyone knows of any more, please let me know, because this is my list at the moment. There's probably more. But most of the fairly standard QA checks look reasonable. Astrometry and brightness scale, at least at the highest scenario, look fine. And with an initial cross-match to GleamX and RAX to do some really simple source modeling for very isolated compact sources look pretty reasonable. You can see the extra frequency data point doesn't really do a whole lot in most cases, but there's a few instances where having that extra point between those two surveys can be quite nice to give you a bit of confidence in where the peak of the curved spectrum is. So that's pretty much where we're at. There's some more validation work to do, of course, a few bits and pieces that I would like to get some time to do. There's some potential changes to source finding that could make some of the spectral modeling stuff a bit easier, particularly if we use the prioritized fitting approach instead of just an untargeted source finding approach. And there's also the question of where do I want to put these data? Of course, the catalog would make sense to go to Vizia, and HIPS images can go to wherever Aladdin hosts their stuff, I forget. But there's also about 6 gigabytes worth of mosaic images, which is actually not a huge amount of space, which is nice. But I'd like them to be served somewhere as a cutout service. Yep, I'm looking at you, Greg, or perhaps other places as well. There is also potential of feathering in low-band GMIMS data, and GMIMS is the Galactic Magneto-Ionic Medium Survey, which covers most of the sky in various frequencies, and the low-band south portion is done with Miriam, CSIRO's Parkes Radio Telescope, and that is has a nice little bit of the band that overlaps exactly with our data, and some very initial, very quick and dirty results of that look very nice. So it's a potential way to improve the larger scale structure that we might be interested in as well as part of the survey. So I'm going to stop there, and yeah, any questions, feel free to ask them now or later. That's fine too.
Questions? Pressing the road around or?
Yeah.
I'll repeat it.
So using the side lobes, very nice. Is there any plans to possibly think about taking some more data, either using the side lobes or concept of imaging to actually better fill in the black hole?
So I had been considering just imaging all the side lobes from all the observations, but of course that's just extra work. There's. Oh yeah, sorry. The question was, is it worth using side lobes to fill in other parts of the survey, basically?
Well, I was thinking about adding new observations to actually better fill in the.
Oh, using new observations. So for one, I mean, we can't add in any more phase 1 observations. That ship has kind of sailed, I think. But potentially, but I think. I don't actually recall why there wasn't South Celestial Pole observations or anything, and yes, yes.
Right. I'm saying use the side lobe trick to actually target the pole.
Oh, I see what you mean. Okay, so point it somewhere where the side lobe would be in the right place. Oh, okay. Well, actually, I think there might actually be more side lobes already. And some of the other declination strips that would potentially fill in that gap. This is one of those things where I can only put in so much work into this project, and there's, the sensitivity ripple is very minor to me, so it may not be worthwhile. It is worth noting too that the side lobe images, while they're pretty good, I'd still prefer not to rely on them. And in this case, it was just because I wanted full coverage for the survey. I probably wouldn't do it otherwise.
Two quick questions. As you do this, some difficulties we have in calculating further observations and so would you now you have this complete catalog? Would you suggest we consider using that as time?
So the question was, Ramesh has been having trouble calibrating close to 300 megahertz pulsar observations, and whether it's worth using this 300 megahertz catalog as a sky model. I would suspect yes, but I'm not sure that it would provide much of a better result than what you might already get with Gleam. I suspect it's going to be pretty similar for calibration purposes, but I mean, you can certainly try. So the question here is the 30% of the infill calibration works. What software are we using for infill calibration? No, so this is I'm still using Andre's Calibrate tool. I haven't moved yet over to Hyperdrive or anything else, but recent talks have certainly motivated me to finally make that plunge. Although I have tested it before and it works obviously excellently. So there's really no reason not to, except to actually find time to do it. But no, not RTS. No. Yep, and there's an online question from Natasha. Well, actually, I think it's more of a comment. No, there's a comment and a question. Okay, the first comment is Gleam's flux density scale is not great for very low declinations. And yes, I'm aware of that. So the flux density scale error and uncertainty is going to be obviously a lot higher in the south celestial pole region. And the flux density scaling there actually is done because it uses the question is how to do the flux density scaling in the south celestial pole region. So it uses the same corrections that we use for the main lobe of the zenith scans, which because it uses the same calibration solutions, and my assumption is that the fluctuations are due to the calibration solutions, then it should be fine. And I did do some checks as well to look at the position dependence in those side lobes, but I didn't see anything wrong with that. The primary beam seems to be doing actually a fairly decent job for those side lobes, so which was quite nice to see. So I'm not concerned too much about it beyond the, I think, 20% or so uncertainty that's already there from Gleam. And it's going to inherit that, of course.
Any more questions? Just ask Natasha if she wants to come up mute, so make sure she's still got her hand up.
Natasha, I see you have your hand up. If you wanted to just say stuff, that is probably fine too. Nope, that's all right. Okay.
One of these slides, you have this strange jumps of flux scale from like day to day or what? Yeah, from day to day, I think. So do you understand?
So it's
jump like due to some extra RFI signal.
So it's yeah. So the question here is on these jumps in the flux density scale as a function of time, but they're not and where they come from, but it's not per day. So each of these two plots here are a full day of observing.
Oh, okay.
So there's like little jumps within a day. So I think this is really just related to this calibration process where we apply one solution, which might work for quite a few obs IDs before we switch to a new solution. And that solution might have had all sorts of potential issues in the sky model that is going to be sort of carried through those observations.
Which is quite a lot at this frequency.
It could be that too. I'm very heavy-handed with the flagging here, and probably more than I need to be, because that was one of the initial blockers, and in fact, that's where some very early discussions with Jaden were very valuable in actually getting the flagging strategy to produce any images. So that could be the case as well.
That's just another comment.
Okay. Yeah, so there's a comment from Natasha here about I'm only currently looking at the 30 megahertz full band. I'm not looking at the individual subbands that we would normally do with Gleam. And the reason for this is partially because the sensitivity is a bit lower generally. And also the fractional bandwidth, as we get up to 300 megahertz, is a bit smaller. So those small narrow bands become a little bit less useful. Plus, it's more work to do more bands than one. So there's that too.
All right, so if there are no more questions. Thank you, Stephen.